Hello, I am İsmail Sengor Altingövde, and today I'm going to present our work, Supervised Learning Methods for Diversification of Image Search Results. This is a joint work with Burak Gönlük from Midwest Technical University of Turkey. So search result diversification is a well-known problem, and in the context of image search, there are even more exciting directions, as the diversification is not only conducted with respect to the topical dimension, but it can also be done considering the visual properties of the images. Let's consider the query Hagia Sophia, Istanbul. On the left-hand side, we see the images that are very similar to each other. These are non-diverse search results. In contrary, on the right-hand side, we see the diverse search results that are taken inside or outside of the Hagia Sophia in nighttime or daytime. And obviously, they could be more appealing to the end user. For diversification, there are several proposals in the literature, and in this work we focus on the implicit diversification methods. MMR is one of the pioneering methods, which in each iteration selects the document that maximizes this formula. The left-hand side of the formula is the relevance of the scored document to the query. The right-hand side of the formula represents the diversity of the scored document from those that are already selected to the final ranking S. Assume that we have already selected these two cats to our final ranking. Then the remaining four cats will be scored using this formula. And in this case, this cat is relevant to the query cat, but obviously similar to that one. So we'll have a low diversity score. Same for that one. This dog will obviously get a high diversity score, but unfortunately it is not a cat and will have a low relevance score. Finally, this last cat is both a cat, so relevant, and furthermore, it is different than the already selected ones, so should be the one selected for the third place. MMC is an improvement over MMR, which not only considers the images selected to the result set, but also those that are remaining in the uh, candidate set. In particular, while scoring a particular image, let's say this white cat, what it does is it considers its diversity with respect to the selected images and also the possible maximum diversity with respect to those that are in the candidate set. That is kind of a feature diversity that can be achieved after selecting this white cat to the result set. MST is a simpler approach in that it chooses the pair that maximizes this formula, that is the total relevance, and the diversity of the pair should be maximized. In this example, for each pair of the images, the formula will be computed, and this pair with the maximum total relevance and also maximum diversity is likely to be selected. Finally, R-LTR is the work which we also base our improvements in this paper. R-LTR is also very similar as it employs an MMR paradigm in a supervised fashion. So, instead of a single relevance and diversity score used in the MMR framework, here there are several methods to compute the relevance score or diversity score. That's the overall formulation. Here, Xi represents the relevance vector, so relevance of query with respect to the scored document. Maybe this one computed using PFIDF, this one computed using PM25. And on the right-hand side of the formula, again, the diversity of the document VI with respect to the set S. While computing this score, there is a matrix for pairwise similarities of documents for each different type of method or feature. So if dx and dy are in the set S, then the diversity of di from these two are computed and aggregated with the function as h, and it is here the first score. With respect to other methods, let's say cosine, Euclidean, Jaccard coefficients, etc., or other features, there will be more scores here. So R is indeed a tensor, three-way tensor of such matrices. The weight vectors omega r and omega d are learned with stochastic gradient descent, and the ground truth is based on a greedy selection of an evaluation measure such as ST recall. So what we propose in this work is, first, we make a straightforward adaptation of R-LTR to do image search diversification. As image similarity or diversity can be computed using textual or visual features, what we do is we separately represent them in the formulation of R-LTR. This obviously provides us some flexibility, as we can only use textual features, visual features, or both, and while doing this we can employ different H functions while combining, aggregating the diversity scores of different feature types. As a further extension, we also adopted the MMC paradigm into the R-LTR framework. Remember, in MMC, the possible feature diversity is also taken into account. So the original formulation here in the previous slide is now extended with future possible diversity with respect to the textual and visual features. Note that while computing this, for a given document image that is being scored, we consider the most diverse image that remains in the candidate set. We also like to note that our approach here is the first supervised approach that is beyond MMR paradigm. That is, most of the related works in the literature following R-LTR employs the MMR paradigm, so this one is different also in this sense. While learning the R-LTR feature weights, we employ a neural network framework, namely PyTorch's neural network framework. So we implement the original formulation R-LTRMMC and R-LTRMMC first using a single layer perceptron without any hidden layer. Secondly, as we are using a neural network framework, we take the liberty to introduce hidden layers. So we go beyond the original linear formulation, and we call this version as R-LTRMMC. Our experiments use a dataset from the well-known media evaluation campaign, and in this dataset, queries are landmark locations like Golden Gate Bridge or London Tower, with 30 training and 123 test queries. Each has up to 300 result images obtained from Flickr together with the relevance annotations. In our experiments, we did the typical preprocessing like face detection or geographical filtering. We used a representative image to compute the relevance scores, and we used several textual and visual features provided in the dataset to compute the diversity scores. As the baselines, we used the original ranking as well as the MMR and MSD methods. Note that these methods use the same set of features, with a basic weighting approach shown here. Here are the experimental results. As you see, all of the R-LTR variants beat all the three baselines. R-LTRMMC, the adaptation of the original R-LTR, performing better than the image MMC, that is, following MMR paradigm is more useful here than taking into account the feature diversity. And finally, the neural network version with a hidden layer of the R-LTR image is the overall winner. It provides up to 11.4% improvement over the best baseline MMR, which is a statistically significant improvement, and also provides around 1.1% improvement over the R-LTR image. Also note that our result is better than 9 out of 10 submissions in Media Eval 2014 that employ the same features like us. As a result, our main contributions in this work are adopting R-LTR for image diversification using a neural network framework. We showed that MMC paradigm does not help to improve diversity, but the nonlinear variant R-LTR image MM is better than the original linear approach. In our future work, we aim to train our models by direct optimization of the evaluation metrics. Thank you for listening. Please stay home, stay safe, and send us your questions via email. Thank you.